Okay, so there's no final, so whatever you're learning here is just for fun, right? So that's I hope that's clear. Um, so for all the Jupyter notebooks, they were all done so that you could do them on a reasonable laptop, like even a laptop from a few generations ago, because I didn't want to go, here, why don't you train a convolutional neural network on these couple of thousand pictures and have it and watch it melt, because it is really, that's orders of magnitude more computation. But I did want to talk about it, and since I'm an astronomer, I'm just going to gleefully go ahead and just talk about galaxies, because that's what I do, and talk about how we use, or interesting things that I've seen convolutional neural networks being used on. So that's it. Hey, fun things that we could do with convolutional neural networks. There are some Jupyter notebooks that I've encountered, but feels a little pointless to give them to you, because you have to either become a member of Google Colab or get an account on Amazon services or something. And yeah, I'm pushing off on that for now. So quick request that if you have worked with the machine for physics, if you've tried it out, it'll be any comments that you come across, as in like chapter 3 and 4 should be in reverse, or there's a little typo on page 26, right? Anything will be very welcome, because Dr. Acquaviva is finishing this up, and she's super keen to hear how this worked in class, right? So I can say, I think it worked great, but your feedback would be really welcome, if you have time for that, right? But send me whatever you have over email. So convolutional neural networks, this is kind of like I love this kind of stuff. It's like it absolutely says nothing, but it is this wonderful vector art going like, oh, machine learning, the great big black box. So right, the Jupyter notebooks. I do have a good one. There's one of the papers actually comes with a GitHub repository where you can just, here's all the code, which I think is great, right? That's where astronomy definitely is going, and I think most of physics as well, where if you have a project, you do a particular thing, you actually put all your code on a GitHub repository. I haven't talked about this because I'm not yet a proficient or even reasonable novice on GitHub. But I do like the fact that even I have like some repositories. Actually, 390 is a repository on there, where you just put the Jupyter notebooks and then maybe some of the data, just the code, typically not the data, because it doesn't allow for very large files. So there are Jupyter notebooks that go with the examples that I'm going to show you. So there are things that you could do, but step one was make a Google Colab account, and I'm like, yeah, that might be a little much for an hour class, right? So there's a bit of a lag there. And yeah, the first one's free model. Everybody's been there, right? So it's like just when you get to the point, it's like, oh, cool, now I figured it out. Yeah, now I have to pay for it. So it is a bit. We have a good machine here, and once that is up and running and I actually understand how I can have multiple people run on that, then the final project might end up being a convolutional neural network. Sorry. All right. So, and if all goes well, it works great, but there's a big if there. So the motivation is that the data is now comfortably about well beyond what we can ever do, even as a group of people. And so the feature space is, for instance, millions of pictures, billions of pictures is. And so you can see why, if you are Flickr or Google or Facebook or, I don't know, what's the more recent social media, name your social media, social media du jour, Instagram. Instagram is just a giant pile of pictures, really, but you want it to tag automatically, right? So this is the kind of thing where this originally came from. There has, of course, I considered having like a little discussion about the ethics of these kind of things. I hope you notice that I keep bringing that up, because you go like, yeah, it's just perfectly fine to train something or optimize something that it identifies cats and dogs. What could possibly go wrong, right? But it's the kind of thing like, yeah, that same infrastructure could do other things. And so that is something to always keep in mind, right? Whenever you're doing these new technologies, what could a malicious person or a greedy person also do with the same thing? And so convolutional neural networks, convolution, you all know what convolution is at this point. You take a function and multiply it with another function, multiply it by a function. You did this with quantum a lot, or you have like this Fourier transform. So convolution is like you have transformations, and then neural network is basically all those neurons that refers to. You have these initial neurons, and then there's a bunch of the next layer of neurons, and then you have an output layer of neurons. This is kind of the simplest neurological model. That's where it came from, because we have several trillion. It is more than stars in the known universe or observable universe. So we have quite a number of connections in our brain between every cell and every brain cell and every other brain cell, right? And that's what this is supposed to mimic. That's where this comes from. And then they realized that, hey, you can actually use this for stuff. Let's try some things out. So, but it can do a few things. Like it can classify something, which is the example that I kept saying, like cats or dog, right? There's just labels, just sticking labels on things. Desk, chair, more chair. So that's one way of classification, right? There's a very clear yes/no question. Or you can make a prediction that can be either single values, or you can do things like, it doesn't have to be a single value, right? It could be a vector on its own. So it could be a string of numbers that comes out. So essentially an image goes in and a string of numbers comes out. And so it can, instead of saying, for instance, man or woman, it can go man, age, likely, weight, height, like all these things that come out of a picture that you could actually guess from a picture. It doesn't have to be a single thing. So that's also a regression that, as we've been talking about it so far, has been, I'm fitting it and I'm fitting one number, but it doesn't have to be one number. So I have the game today is or regression. Okay, so that's the question that comes up every once in a while. So we can either do classes, a range of values, just one value, that's that we typically talked about, or it could be a vector. That's also regression. Okay, so the convolutional part is where you take an image, you take an image and like, here's every pixel, and I'm taking all of these and I'm turning that into like a single value. That can be like, here's a line, and so now this box says, there's a line, I'm the line box. I'm going to check if there's a horizontal line there. And so it goes 1 when there's a perfect line of 4 black pixels and like 3 white pixels on either side. Right? That's one kind of neuron. It can go look for just that. Other ones are, this one's black. There's like, I'm the dot neuron, right? So I'm going to look for this, and like all of these are white and that's black. Then I turn like, bing, I'm 1, and otherwise I'm 0, right? So I scan bits of the image for just that. That's what a kernel is. That's what a convolutional part is. Filters or kernels, right? So this is something that is in the imaging Jupyter notebook, where you kind of like, oh, I can filter something, right? Or I can smooth something, but like that's exactly what's happening here. So what you do is you start with an image, and it basically goes through a layer the same size of the input feature. It comes in and it basically goes, oh, there's this many dots in these places. There are this many lines, horizontal lines, vertical lines, arc-shaped things. And so these are basically all common features in images. So it doesn't make any judgment on whether or not it's a cat or not. It just knows there's like a curved bit. There's a curved bit, so the neuron for curved bit goes on when that image shows up. Now, so these are kind of common kernels, and then it gets stepped down. And so that's the part with like, that's called max pooling or step down, where it gets averaged over larger chunks of these kernels. And they get kind of, so the whole layer becomes, basically gets reduced to a quarter of that, and maybe to another quarter, and then to another quarter. So there are these step-down functions basically to reduce the amount of information down to the essentials. Okay, so you average out over every 4 of those neurons to get to this layer. And then you train a couple of more, and then you step down again. And then you train a couple more, and then you step down again. So these are training steps, and then the max pooling is the red one. So that's basically where it's averaging out and just reducing the amount of information that's coming through until you basically are, there's just, one layer, and this is the output. Like here's a couple of more training, and then that's the actual feature that you're getting. That's the function that gets spit out. Right? There's either the one number or it's like a series of numbers. So the whole trick is that you have something that you train here, and basically every black box is something that you adjust with every new image that you run through it. We'll get to in a bit, but it's like you have different speeds for like the big ones, and these you can adjust with big swings or small swings, right? So some of them you don't need to adjust, or maybe not at all, and some of them you need to adjust quite a bit in order to train them up, right? Okay. So you have input pictures, and you have the output, which could be either the outputs which in your training set, so you got a picture and you got a label, right? So it goes, okay, this one convolve, subsample, convolve, subsample, convolve, subsample needs to be over here. That's a robot. And then the next picture is like, that's a human, convolve, subsample, that needs to be on the other side, right? So you can do the cat dog thing, right? And every time you need to adjust the weights so that it actually gets there, right? Because it's your training set. So you go over many of these. And so you can already see why this is becoming such an onerous task for even for a computer. Because you're doing lots of these convolutions, you're doing then lots of subsampling and more convolutions and more subsampling. This is all happening in computer memory and lots and lots of computations. The data isn't that big, the number of computations is. So the funny thing is that what happens with the science for a long time is that we just got aggregating more data. So our biggest concern was, do I have enough disk space to actually keep all my fresh new data? And the only computation that I did on it was like a chi-square fit or something like that, right? So I got 1,000,000 points, but I'm really only using them once. Here, it's like I got 1,000,000 points, but I'm computing them also 1,000,000 times. So suddenly I don't know, it's not so much a storage issue, it is how much computation can I do? So that switch would be like, oh, I need to actually do lots of computations on a same set of data, meant that suddenly there was a much more interest in, like, okay, how can I have all of it in my memory and then lots of computations on that? Well, it turns out computer already doing that. That was called the graphics card. So enthusiastically, everybody hoovered up all the graphics cards, made a whole rack out of them, and started doing this. So that's the difference between, this is why it's like, oh, why do people call it GPU computing, graphical processor unit, right? It's all because those were optimized for the same image, but lots of processing on the image. So the steps are, you filter, you do the kernels, you subsample, more kernels, more subsampling. So the choice of how many layers do I stick in there, and how many times do I step down? So that's all hyperparameter, essentially, right? So it's all designed how this is going to look. And so you can already imagine that these are 128 by 128. So that's my first sets of kernels. So, all right, fine. And then I need to step down and step down again. So there's a bunch of kernels and learning layers there. So figuring out what you need to do there is your first step if you're trying to do a convolutional neural network. The other part is like, what label did I want? Before you just get lost in, design space. Do I want a label or do I want a value? Is this important, right? Do I have enough labels? So how much should every layer adapt to every time it learns, right? So the way that happens is that the convolution, the very first part, you do the lowest rate. It doesn't, because they're all kind of typical of images, right? They're not, they don't care it's a cat. It's just looking for that dot. It's just looking for that curved part. It's just looking for that. So these are common features in images. Google actually makes their lowest layers astronomers, because like, yeah, we have a first layer that's trained completely on everybody's pet images, but they work just great on galaxies because they have the same common features, dots, stripes, that kind of thing. So this actually needs to learn the lowest rate. This needs to learn a medium rate, and the highest rate is actually the end. Often what people end up doing is they go like, well, this I can just adapt from something else. This is something that I'm already trained a bit on something very similar, and then only the last bit gets done for a new feature, for example. So that cheapens the, so there are all these little tricks, like, for example, well, this already exists. Well, that saves me a ton of time, a ton of computing time. So that's what happens with these layers. So that's the nice thing when you go to Google Colab, like that layer is there just as a import. So first one, typical convolutional neural network, galaxy images. All right, so you can't see them. So I'll do the same thing. I know that I'm going to put somebody to sleep at the dark room, but there we go. So you have these images of galaxies from the digital sky, right? The first digital picture of our entire sky, or a good part of our sky, and we're turning them into metallicity, right? And the metallicity being, in astronomer terms, we've got, this is the, all the elements, the periodic table, and as far as astronomers are concerned, this is all metals. So you've got hydrogen, helium, and stuff. So the good news is that we can just express that as one single number. We want to be very honest, we just measure oxygen, because we can't really measure most of the other ones. But that's a thing that we want to be able to predict. It's still hard to do that because you need to find an emission line or absorption line for all of them. Oh, that's the wrong one. So in order to find, go find beryllium absorption features in a star is possible. People have done it, but in 2 stars in our own Milky Way. It's hard to do as soon as you're outside of our Milky Way. So we just kind of go like, okay, how much oxygen is there? And so that's the thing that's our prediction, right? That's our metallicity. And we have these images, and so it goes through a feature map. It goes subsampling, that's step down, another feature map, more convolutions, subsampling, and then predict something. I want you to notice that there's 2 numbers at the bottom, and z predicted. And so this is a logarithmic scale. So a tenth of a dex difference is already a fair amount of, like, 2 dex is 0.2 dex is twice as much, right? So it's a logarithmic scale. It looks good on a logarithmic scale, but still, you run all these images through it, and you see if you can actually distill the metallicity out of that. Is that actually something that you can link up? So how things look, does the metallicity know about that? So is that classification or regression? Oh, shoot, he was asking us something. Right, okay. What is it? Is it classification or regression? I have galaxy images. I'm predicting the metallicity. I've got 1 vote for regression. All right, let's do it like this. Who votes for regression? Okay, that's a room. Okay, yes. Any value between basically 0 and 10 or something, but it is like it's a predicted value that I can then compare to the actual true value, right? So I can then see the information I get. We train with many images, and then so it goes through that convolutional step down, another step down, another convolution, and another step down. So the root mean square total is you take the square root of the difference between those two metallicities. And so you know how good you're doing as a sample as a whole, right? So you can do that over all of your sample, or you can do it even for individual galaxies. And so here it's like, here's the true value. This is the predicted from the images. So this is something that you usually need spectroscopy for. I need to take a step back. Why are we doing this? Because if we know what this is, we can just go out and get a spectra of these things, right? Spectra are expensive. It takes a long time to stare with a telescope to get a spectrum, because you're smearing out all the light that you so carefully got with your telescope. Big bucket of glass gets lots of light, and then you run it through your entire instrument, and then you smear it out over all the wavelengths. So suddenly all that benefit of collecting is now smeared out over every pixel. So it gets hard to do a spectrum. Spectra are hard. They're expensive. So maybe we can skip that part, right? Maybe we can do a prediction before we actually go out and take spectra. And so this is the one-to-one relation. And it's not a perfect one-to-one relation to begin with, right? So it flubs a bit at the low end, and it flubs a bit at the top end. But this is pretty good from an RGB image to an actual measurement. OK, so I'm not sure if I dropped the term feature engineering at all, but this is the part of like, these are my features. Which one of these features can I drop? How much information does this thing need to begin with? And so this is stepping down the resolution. So 128 is what I fed it, what they fed it. And then basically this is a quarter of that, and then a quarter of that. So that's a quarter of a quarter. So this one's 16th. And this is 1/32nd, no, 1/64th of the original image. So a lot less information in here. Blur the image, step down the number of pixels. Everything speeds up because now I have less data that needs to go through and needs to be computed and needs to be trained on. So how well do we do? And now if you kind of look at these, the numbers are like basically 16 by 16. They definitely put that in there just to see if you can make like, what happens if I just look at little colorful blobs? The answer is like, it's not a good predictor. But as soon as you have a little bit, so you can actually do this further away, you still do just as well. And the other thing was, so this is where you do the image size, and you had that RMSE, right? That root mean square equation. No, I don't know what RMSE stands for. I use it all the time. All right. This is basically how off I am, right? How far away am I from my predicted values off from the true values. And so you can see like, well, if I'm at 16 by 16. It's terrible, but it drops pretty quickly. And somewhere between 32 and 128, I'm actually not doing so bad, right? So you can look at a curve like that and go like, actually, this is enough information for this kind of work to get me a reasonable result. The other thing is like, this is the color image, and this is what happens if I just used a black and white image. So what happens if I throw color away? Right? So what happens if I throw a feature away, and how well do we still do? And so this is the kind of thing that you do as a sanity check afterwards, because you go like, all right, where was this information hiding? Because what part of the image knew about this galaxy's metallicity to begin with? What happens if I just stamp out the center and I just work with the outskirts? What happens if I just take the central part and not look at the rest? Is color important or not, right? So this is the kind of things like, where is that information hiding? So here's another example from Smith et al. 2000, like right now. You can have images, black and white images, and that's our features. And then our label is the profiles, the radial profile of each of these images. So it predicts, their convolutional neural network predicts what radial profile you would get if you would average out over. You go like, well, that information is in there, right? I know that. But it's kind of tricky to extract that. So can we actually do that using convolutional neural networks? If I have that anyway, it will spit it out automatically, and there you go. The residuals are pretty encouraging. So the question is, classification or regression? right? What are we talking here? If I start with images and I end up with a profile, is that classification or regression? Who votes classification? I got 3, and that means the other 3. It's a tie for classification or regression. Thing is, this is a list of numbers, right? It's not like this is one kind of profile and this is the other kind of profile. We could go like that's an elliptical profile, that's a spiral profile, but that's not what we're getting. We're getting an actual list of numbers as a function of radius. It's actually 2 lists of numbers, brightness and radius. So that's a whole little vector there that it spits out. It's still less information than is here because that's, you know, a 2-dimensional image. Not the kids, so nobody's on fire. Please stop. So, next question, looking for galaxy mergers. Now, maybe you can see the little blue thing here. This is a pretty well-known, it's a pretty well-known a merging galaxies. These are 2 galaxies. These are their tidal tails, and it's a classical example of like, oh my gosh, galaxies do merge, right? As soon as they saw this, even on a photographic plate, 100 years ago, they went like, clearly this does happen once in a while. So galaxy mergers, how often do they happen? This is very clear, but how well can we identify those? So 2 years ago, Chris Pearson did this project where he's like, all right, well, how do we usually find this? And so we reduced these things into to morphometrics, so Gini and M20 for these images, and then we basically drew a line like this seems good. Anything above that, everything below that is a merger, and everything above that isn't. Which is a little okay. And then there was a rival scheme which basically said, yeah, here, and then everything above that is a merger, and anything below that isn't. So that's the kind of thing. It's like you have a feature space, and you just say, here, that's it. And so that's sort of like a classical way of doing it. Now I'm just going to take lots and lots of images, run them with convolutional neural network, and then you have this. So you convolve, step down, and you end up with like a 1 list, and eventually 2 bytes, which says merger, yes or no. So it basically makes a judgment on each and every individual image. Once again, asking the panel, is this classification or regression? What is this? All right, votes for classification. This is indeed classification, right? It's either a merger or it isn't. Now, this is the simplest thing for classification, where you go like yes or no. But there can be different kind of classifications, right? So as long as there's discrete categories, that's classification. If there's basically a sliding scale, as soon as you ask yourself, like, what's coming out of this label? Is there, can I be a merger and can I be like half a merger? Can I be like, if there's like, can I think of it as like somewhere between these things? Or is it literally a step? Is it a bunch of steps? If it's discrete steps, classification. If it's smooth, that's regression. But it's the first thing you need to ask yourself, what do I want from this? Do I want classifications? Because I'm really only interested in class 2. Those are the ones I want. I want a clean pile of class 2s, and that's it. Then I'm going to run with it and do my thesis. Or do I want to know what the actual values are so I can compare them to measurements later? Is it basically a prediction for the future? Yes? Okay, cool. Right, going on to predictions. I told you that this is my, I get to just geek out over galaxies, so I am going to do the right one. Yeah, okay, so this is our this is a Hubble Space Telescope mosaic in 3 colors of the largest galaxy we know. And we nicknamed it Rubin's Galaxy because back in 1980, so now very long ago, she pointed out that this thing was pretty enormous. It's basically 10 times bigger than our own Milky Way. It doesn't look like it. It looks exactly like every other spiral galaxy. It's just gigantic. And so I'm working with a team of people on this. This is our main project. And there's this sort of secondary question. Like we have a main science question, but the secondary question is like, I wonder if there's actually a supermassive black hole there in the center. So the first thing you do is see if there's a spectrum that exists for this galaxy. So if somebody has taken a spectrum of the center because there's particular emission lines, so basically ionization spectrum, if you're close to them, that's a black hole. But like that thing is just spitting out UV and X-rays. So you're talking a really hard radiation environment. So suddenly oxygen 6, right, times ionized oxygen. 3 times ionized oxygen is pretty common. Like there's this whopping combination of them. That only happens if you're sitting next to a really bright source. So question is, do we got a spectrum here? Well, first thing you go is to the Sloan Digital Sky Survey. The Sloan Digital Sky Survey ends here. Our galaxy's in the galaxy. If they only kept going for like one more tile, I would have been happy. But of course they didn't. So no spectra for you. And so if it's not in Sloan, you're sort of, out of luck because it has taken the spectra in the northern hemisphere of just about everything. So if it's not in there, you kind of now have to go to a telescope. Sorry, I have to go get time on a telescope, travel to a telescope, point the telescope, take the spectra, reduce the spectra, and then have a look. Right? Much easier to go, click, my spectrum. I'd much rather do that, right? Although it's really fun to observe. So, the news is that John Wu has once again saved my bacon. He spectra for this. And two machine learning applications. So we learned about principal components, with spectra, where we had like these eigenspectra for the space that we needed. So you can have like an eigenvectors for the orthogonal vectors that describe the entire feature space of all possible spectra. And so that's exactly what they did here. So basically, they encoded every SES spectra into about 6 numbers. And the neat thing then is they took those 6 numbers and go like, all right, those are that's my labels. Those are the ones that I want. That's the thing that I'm going to train my neural network on. Right? So it's a regression technique to give us the 6 numbers. And those 6 numbers turns everything into an SES spectra. You can say this much of this from this much of this. It's basically an ingredient list. And so the input images, lots of images. We have way more images than spectra. But they trained it with a hybrid neural network. So basically, it's again convolutional. And then you can make predictions. I'm like, all right, I got one for you. So you have this training set. Sorry, I skipped ahead. The training set, so you have all these images with different, some of them have these emission lines. So that's where ionized gas lives. Others are just simply stars with some absorption features. That's the atmospheres of stars. And so you have these, some of them are pretty, there's no new stars. There's no hot stuff happening. So there are no emission lines. There's no ionized gas floating around. However, others do. And so you can compare predictions versus, so essentially labels versus observed, right? So you do the exact same thing what you do with machine learning. I've trained this so that it would predict spectra, and I kept a little test sample behind, ran that through as well, and compared the spectra. So you can see the residual. So this is what it is for Rubin. See, this is a typical AGN, like big whopping emission lines, and it's also broadened here because it's at the poles. A quiescent galaxy, no new stars, so no big massive O stars ionizing everything around them. So there's just a little bit of these absorption features that happen. And then there's a star-forming galaxy, so that has, fresh for like 1 million years. So you've got to keep making new ones. And those, the ultraviolet basically pumps up the oxygen, and the oxygen recombines and lets out an emission line, right? Lets out an emission line. And that's basically some of these features here. That's hydrogen and oxygen, basically. So it's not a star-forming galaxy. It's not quite an quiescent galaxy. It's something, it's like, looks a little AGN-y, star-forming something, right? Especially this is from the center of the bit of AGN thrown in, because all the star, which is out. So the prediction is, yeah, there's definitely an AGN in there. You should find an AGN. These are the strength of the emission lines. So we have a full prediction, like we have a whole spectrum that we can compare against. Except that, remember, Rubin's galaxy is a bit of an outlier. It is this huge galaxy, right? So it is not something that this neural network has trained on. It has trained on normal. And so how good does it do in something a little bit weird? Okay, let's check. So this is the kind of stuff that I do. Like, oh, cool. We have a prediction. I can observe this. Let's go. So you shake the tree of astronomers you know, and end up with here's a scan of my 1983 spectrum from. So I'm like, oh, cool. That's one. You just ask people nicely. Honestly, a big part of science is just asking people nicely. And suddenly they go like, oh yeah, here's my data, no problem. 90% of the time they're thrilled that somebody else actually can use this. So not a problem. Feel free. Like, I'm short on data. Could you help me? We'll get you quite far in science. Because then they go like, yeah, great. And if anything comes out of it, yeah, you can be co-author. That's fine, because you made the data to begin with. Just ask. If it's not already online. Got MMT's telescope. Went out and observed. In fact, the black line is what the machine learning algorithm predicted, right? So we have this for all these different spectra. Some of them don't go all the way. This one didn't go all the way down to the blue end. But they all are pretty much on the money. The emission lines are a little bigger here. About it, but this seemed to be pretty well. The fun part here is all this particular algorithm about 10 times bigger than the Milky Way disk spectrum for the center. So this might be a neat way to get cheap spectra. So you can do things like, what are the emissions predicted line strengths for this particular galaxy? What is the predicted? So you can make predictions based on a training set and say, this is what I'm expecting. And whole corner over here. Because we're asking, I'll just go, with signal to noise, and then I can go do this new thing. Gets you to be more efficient. Now, I've been saying for the last 8 weeks. So it's a tool. Again, what's this classification? Regression. Voting for classification. Series of numbers. You can look at what you actually observe as far as these emission line ratios. So there's oxygen, nitrogen, silicon, and more single ionized oxygen and hydrogen. And these are commonly observed emission lines. You can see what the ratios are. And so some of these are predicted. And the green one is the one that's the observed So yeah, they're still a little off, but the red one is observed with a similar size aperture, and actually we're pretty on the money there. This is just looking closer at the nucleus itself, and it's like, yeah, there's definitely an AGN happening there. So that's actually pretty neat. All right, so that was my, hey, I get to have fun with galaxies and machine learning. But as you can see, I don't actually do the convolutional neural network training just yet. I feel like personally for me that's the next try. I work with John Wu, who's way better at it, so it's like, yeah, I can have him do it, and just he tells me where to look, and I'm like, cool. So I'd like you to do for me is if you have any left sitting on your archive somewhere, please put them in so I can grade them. And then secondly, can you email any comments on the book to me so that I can compile them all and to Dr. Quiviva? And could you please fill out the class evaluation? That's right now, and really that's the kind of thing that I'll be evaluated on. And this October is my tenure case, so I would really like it if everybody actually fills it out. But yeah, that's it. All right, thank you all for coming. Thank you all for voting. And are there any assignments that I can help anybody with, or are there any issues that are remaining? Cricket. No. Are we good? All right, then I'm calling it. Thank you for coming to Physics 650. I hope you guys had fun. So.